from. Neo4j is a database company, so we build a graph database. I'll maybe do a little bit of an explanation of what that is. And the idea of this talk was to kind of give like a sort of a summary. So I guess I'll maybe show you the agenda. So the idea was sort of talk you through some of the things that we're seeing people doing, connecting the worlds of graphs with the worlds of machine learning and AI. Talk about like what particular role graphs can play in this area. And then we'll sort of run through examples of things that I've seen customers of Neo4j doing, prospects of Neo4j doing, and then we'll look at some future areas where people seem to be focusing the research. So that's the idea. So I'm not an expert in a definition of artificial intelligence, but this is, I think, a reasonable one to go on if we were trying to like position it. So the idea is that we're trying to build some sort of process that mimics human decisions. I guess that's like the high-level explanation, and then if we zoom down, we have something more specific that we can focus on. So we get into, and these are like the reason I picked these particular things is we'll cover some topics in relation to graphs later on. So we'll look at machine learning. So this is kind of like how can we build some sort of model that's able often to predict something, either classify some data or predict like some value. And we'll probably do it by feeding in a bunch of training examples. And then we'll also look at deep learning, which is the idea of sort of trying to mimic the neural networks in a human brain to do a similar task. And so in this diagram, machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. And there would be obviously many other things that fit in under these categories, but we just... Okay, so imagine instead of a real child, we have a cartoon child. And so the idea is, imagine we have a child, and they're like, so I have a daughter who's 18 months old, so she's kind of attempting to do this process now. And imagine they come across, they see like this cooker, and they're like, oh, cool, I should touch this cooker. And then they burn their hand, and they're like, oh, that wasn't a very particularly pleasant experience. And the analogy that you probably see sometimes used is that for a machine learning algorithm to learn this, it then has to go and go, oh, maybe I should touch my hand on every single thing that's hot in order to create enough training examples that I can realize, oh, yeah, maybe I shouldn't touch these things that are hot. But it would be cool, and humans can do this, that they can use the context of something they learned elsewhere to realize, hey, when I see a motorbike's exhaust, I shouldn't go and put my hand there because I already learned that hot things burn me. And so this is the idea that there's some context that we have in this example in human interactions, but can we do the same thing with data? Like, can we figure out what's the context of this data and use that sort of the context that we have to make better decisions without having to go and create loads and loads of these training examples? One area that people are doing a very similar type of thing is representational learning. So trying to transfer learning, I guess, trying to take something that's learned in one domain and apply it across to another domain. But in this case, we're looking at another approach to that problem. So we call it contextual learning. So we're not there quite yet. So we have a look. So what are we missing? So often the data that we're working with is very flat, and it doesn't really take any context into account. We're often missing the context to make the right decisions. And on some machine learning, in particular deep learning algorithms, we get the result out of kind of a black box type thing, but we don't really have any idea why was that decision made. And so this is this sort of, so these ones I'll show you like some examples of what we've seen people doing already, or the top three. And then for the last one, this is kind of an area of research where people are trying to figure out, okay, we've got this deep learning neural network and it's given us some result. We don't really know how it came up with that result. Can we sort of start to figure out how we might explain that to the user? Yeah. Yeah.
Without some kind of explanatory framework, you can't actually verify that the result is right.
I think maybe for that one, it kind of depends on what the decision you're making is. Like if the user doesn't, I mean, I can't think of something off the top of my head, but yeah, certainly for some decisions that a computer might make, you want to know, well, how did you cut? Like if you reject a mortgage application, I want to know, well, what made you reject it? But equally, I can imagine there are other things where the decision is smaller, and you're like, well, I don't really mind.
I mean, when you think that if you go to a supermarket and buy a sausage,
Yeah,
these days, consumers demand traceability of that product right through its supply chain
yeah.
to the origin, right?
But
And
that's
an
yeah.
extreme example of wanting the audit trail, which shows how much importance is attached to that.
But I mean, I would say for like tracking like the provenance of where some food came from, that's kind of like another problem than trying to build a model to predict something or recommend something.
It's an analogous problem because it explains that people don't just want to be told this is the right sausage; they want a lot more. Right?
Hmm.
And you only have to go to the autonomous vehicles to realise how big a problem this can be.
Yeah.
Sorry for commenting on that, but going to the autonomous vehicles, I just want to rephrase. I think it's a very important topic, the fact that we can trace back what are the decisions made.
Yeah.
But what is more important, that we can trace back what is the decision that it's making, or that what is the performance of that decision? So if an autonomous vehicle kills 10 times less or 100 times less people than humans,
Yeah.
do we prefer to have these autonomous vehicles even if we don't know how they work, or do we prefer to know how they work but have a higher ratio of death?
Yeah, I don't know. You'd have to ask someone who works on autonomous vehicles. I imagine. I'm sure they must be thinking a lot about this. But I would expect you're probably right. The second one is more likely. But I mean, I don't know anything about autonomous vehicles other than what I've seen in the sort of popular talks about them.
And just quickly, there's a problem between correlation and causation.
Yeah.
In as much as that, if you rely too much on correlation, you can't really explain why things are happening necessarily, and you will find that the correlation isn't conformant all the time, whereas causation should actually be a fairly traceable path to show why you arrived at the point that we can trace. You say why. Now, somebody the other day said, you have now to be able to do that because of GDPR. The process requires all decisions to be traceable.
Okay.
So if you rely on correlation, there's a weakness.
Okay. I know what GDPR is, but I'm not sure that I followed like how exactly those things are linked together.
Well, on the basis, explain to me, that with causation, you can say there's a direct relationship, and that's why we're guiding.
Okay.
And if someone says why, you can actually list out all the decision points
Mm.
and which directions taken, and that satisfies most people. With causation, there's with correlation, there's there's a 60% chance there'll be this and a 20% chance there'll be that.
Yeah.
But not showing any reason for making a particular decision. Sorry,
Okay. Yeah.
Let's just log that point and move on, shall we?
Okay, right. So let's go to the next point. So the idea is that we've been sort of trying to, I guess, curate what we've seen people doing with graphs in this sort of area, and they kind of the categories that we've seen people doing stuff falls into like roughly there are 4 categories. So one is sort of we headline that connected feature extraction. So this is like, can we if we're just building a normal, like a standard machine learning model, can we extract some features from a graph that we can feed into such a model? So we're kind of like trying to like, and those, I guess we'll go into each one in more detail when we get there. So that's one. Second one is graph accelerated machine learning. So like can we experiment with more different models by storing the data in a graph? So like, can we improve the speed of the machine learning pipeline? So we've observed some people, the way that you can model data and store data from different data sources together allows you to sometimes speed up the number of models you can try out. The third one, and this is the one where people have done the most, at least publicly published stuff so far, is in the area of knowledge graphs. So this comes under another type of AI. And then finally, we've got the AI explainability. Now, so far, I guess this one in the bottom right-hand corner is the most interesting to people. This is also the one where where the least progress has been made so far. There's much more, many more examples of things that work in the other areas, and this one is kind of a thing that everybody is trying to solve. So if we go to the first one, so let's have a look at connected feature extraction. So feature extraction in general is the idea that I've got some data and I want to effectively, most machine learning models take some sort of matrix. So like a lot of so if you've ever so Kaggle is a machine learning or data science competition website, and they give you these data sets, often in CSV files, and you have to train a model to predict like say a value, so it could be like a house price, or you have to try and categorize something. And they give you all these pieces of data. So like, for example, one common one is the, say the Titanic. There's a Titanic data set, and they go, hey, here's all the people who were on the Titanic, and a 0 indicates that they were alive, and a 1 indicates they died, and here's a lot of information about that person, and it might include things like what class ticket did they have, how many family members did they have on board, which port did they get onto the boat, and loads of other sort of basically like properties that you could feed into that algorithm. And that's like the typical way that people build these machine learning problems. So everything the data is all flat, and it's kind of like a matrix. So you have all your data items as rows, and all the individual like pieces of data as columns. And nearly every single problem here, the data is flat. There are no relationships between anything. It's all kind of pre-computed, and it's like, hey, here's all the data that you need. And you can't bring in, there's no relationships between anything. But for some problems, there are relationships that you can use, and certainly not for the ones that Kaggle point out, but for some problems, relationships are actually better than just having your kind of flat matrices and relying on building these matrices or tensors just from data in tables. And we've seen that like either using data directly from a graph or from a graph algorithm that runs over a whole graph can actually give you features that are very useful. And I'll show you a few examples of things that we've seen people doing so far. So this is the idea. One domain where it seems to work quite well is financial crimes. So we've got 3 methods. So we've got, but they all try to solve the same problem, which is I've got to get some features to feed into my machine learning model. The first one is, well, can I just work something out by just doing a simple graph query? Can I work out like the number of relationships of a particular type that a node has? Or can I work out how many nodes with a particular label are nearby to a node at different degrees of separation? So that's one. Second one would be, can I run a graph algorithm? So graph algorithms are algorithms that run sort of over a whole graph most of the time, and they typically give you a value or a label. So those are the main 2 that we look at in this area. So I'll explain some in a little bit. So that's the second one, and these are still giving like individual values, both of these. The third one is graph embedding. So if you're familiar with word embedding, so this is word embeddings are the idea that I have all these sentences, and I can feed them into kind of a machine learning model, and it will give me back sort of an array or vector of numbers representing each word. And this is, can I apply that same approach, but to a graph instead, so that where the structure of where that node sits in the graph results in some sort of vector representing it, and you can compare those vectors against each other to compare the nodes against each other, or you can just feed the resulting vector as your input into a machine learning algorithm. So those are the 3. And on the other side of the slide, we see some of the use cases where this seems to work reasonably well. And obviously, like the use cases where it works, if you've got a domain where there are no relationships between anything and everything is really flat, and you can figure it out just by doing simple sort of aggregations or computing or feeding in properties, then you don't really need to add these features in. But for some domains, such as transaction fraud here, so we've got a couple of other different types of fraud, and anti-money laundering, sometimes these algorithms are very helpful for finding things that you can't find from other methods. Yeah. So imagine like this is just a simple one. So imagine we're trying to do some fraud prevention. So we want we've got a graph here, and we want to, and so you can see what's on here. So we've got account holders. They're connected to phone numbers that might be connected to another account holder. The account holder also can be connected to a bank account and to a credit card, social security number, and you can see there are some other things on there. And maybe we're trying to work out how many fraudsters someone is connected to at different degrees, and so we can quite easily count like how many are they, like, so graphs are very, so I guess in the graph model, maybe I'll quickly explain how this works. So in this example, the things in circles are representing what we call nodes. So those are like your main bits of data. So in this case, we've got an account holder, a phone number, a social security number, and then the way that they're connected are what we call relationships. In this diagram, the relationships don't have what we call a type, so you normally describe what is that relationship. So in this case, it would be the account holder has a phone number. I guess most of these could be maybe they secured a loan, maybe they were given a social security number. And so you can do, the idea with graphs is that slightly differently than how relational databases store data. So in a relational database, effectively each one of these lines is a join that you might compute when you run a query. In a graph, it's stored when you write the data to the database. The join is stored. Which is?
I mean, normally you'd have an account holder.
Yeah.
Table,
Yeah.
some key, and then you'd have phone numbers as a attribute column that's got a functional dependency on the key.
Yeah. But then the actual join itself is computed when you run the query, right? So there's not, it's not actually.
Necessarily, because it may be an attribute in the table.
If you did.
When you go from one table to another, you're doing a join.
Yeah. So that's the example I'm describing.
It's a functional dependency, therefore it's a functional inference that you're making. Join is a fairly ineffective way of making functional inference.
Okay. Well, I'm not the expert of relational databases, so we'll go for. We can replace your explanation for my explanation for that bit. But the rough idea here is that in the way that the graph is storing these data, what we see is that if you've got queries that make use of following lots of these relationships, it's able to do those type of queries very quickly. And we can change like how far it looks. So we can do what we call variable path searching. So I can say, hey, from this account holder, go and look at, so level 1 would be just go out to here. So these things what we call level 1 from the node. Level 2 are like, okay, go to a node and then go to anything connected to it. So that takes us, on this side, it doesn't go anywhere. But if we went here, we can get out to there. And then we can change like how far do we look. So effectively every time you change like how far you're looking. So if we look at level 1, I guess if they were in different tables, you could consider that as one join. If you go at level 2, okay, we're joining again. Level 3 again, and we might then say, okay, a feature that we're gonna pull into our data set is how many account holders are we close to us at level 2, maybe, and then how many at level 4, and we might then use that as a feature in a machine learning model. So that's just a simple example of what you might use it for. Another one that we've seen people doing is computing the PageRank score of people in a graph. So PageRank is a kind of transitive influence algorithm where nodes kind of give credibility to other nodes based on having a direct relationship to them. And so you can use this to compute which nodes are transitively important in our graph based on who is connected to them. I mean, this is a very, very narrow part. No, I'm staying like at a high level. I'm not going to. I'm
saying that knowledge of these relationships makes you more effective or faster at doing the fraud detection. I'm struggling to see how that works.
No, I'm not saying that. I'm not a fraud expert either. I'm not a relational database expert. Not a fraud expert. I'm just saying one thing that we've seen people do is in fraud. One feature that you can add in a fraud use case is, can we work out features from a graph and feed those into a machine learning algorithm that might be being used to compute fraud? So it's not the only feature. I'm sure there are other features that are completely unrelated to a graph, but it's.
For example, find links between accounts where there are covert transfers
Yeah.
Typical frauds have very long trails, so it's hard
Mhm.
to trace them. It might help you do that.
I mean, one we see that so the problem with talking about fraud stuff is once people figure out a way to do it, they do not want anyone to know how they did it. So they tend to be very secretive about what exactly works. So you kind of only get sort of generic, hey, this thing kind of works. But one like really simple thing that we've seen people doing is, and you sometimes see this in kind of open data sets, is it would be like, so it's not so much on this diagram, but maybe two people sharing a phone number or an address is maybe not that unusual. Let's say an address. So two people sharing an address, you could imagine that probably is all right. That might be, there could be people living at the same house, but maybe if it gets to 3 or 4 or 5, then you're like, that's weird. Why are they doing that? And if you're trying to detect the fraud only by looking at individual data, you wouldn't see it, right? That's not visible to you. It's only when you start to look at how things are connected to each other that it would become clear to you that that thing is connected to multiple people. If you're only looking at the individual account, you just see, okay, I got the account, they've got a bank account, there was an application for a loan. It doesn't seem like, so when you're looking at discrete data, maybe only what you notice is, there was suddenly a loan request for a very high amount. So you can see like discrete things, but you can't see like, there's something weird going on here. Why is this phone being used by 3 people? Is that like actually a real account, or is this like a fake account, or are they stolen someone's identity, or what are they doing here? So the idea here was not that you take this and go, okay, fraud detection is not solved from this slide, but was the idea that this would be an example of a simple feature that you could extract quite easily from running a graph query. Cool. So, sorry, I went too far. Let's come back a bit.
I'm sure you can. Yeah.
Would this count as a hierarchical database?
Would it be a hierarchical database? I think it is. I think some of the ideas that it has are quite similar to databases that were there sort of 1980s before the relational databases sort of became the only thing. But I mean, I was only born in 1984, so I will have to trust in your knowledge of it, because I certainly didn't use any of them. So just to show you, we've built a library in Neo4j to help people. It wasn't specifically to help people with machine learning feature extraction. It was kind of to help people run graph algorithms on Neo4j. And so these are some of the algorithms that we've put in there. And we have if you want to learn more about these, I guess maybe once I show some more examples, we have an ebook sort of showing how to use them, and then an O'Reilly book as well, sort of going through an example of sort of showing how to use them and showing them on bigger data sets as well. Okay, so one area where this is way before Neo4j was doing anything, so this is like 2004, is the idea of link prediction. And I'm going to only talk, in this case, about link prediction on monopartite graphs, so where the things are the same, so like a friends network or a citation network. There's also research in predicting links between things with different labels. So if I've got a person and I've got a business, can I predict whether or not that person is likely to review the business? But they use some slightly different approaches. But the underlying idea of link prediction here is that we can predict what links are going to appear in the graph in future based on the structure of what is there right now. And this seems to work quite well. So this is quite a nice example of where a graph and building and feeding. So people have taken some different approaches. So one of them is I'm just going to compute one metric, and I'm going to use just that metric to say, hey, a link between these nodes is likely to exist in the future. And then another approach is, okay, well, I'm going to take all these different potential measures of whether or not a link is likely to exist, and I'm going to feed them all into, say, a random forest classifier, and I'm going to try and predict links in that way. And there are lots of papers. If you search for link prediction, there are probably hundreds of papers written on this. So we've got in the book that I described, we've done an example of link prediction on a citation data set. So we've got like a citation data set with a few 100,000 co-author relationships between people, and we cut the graph on one of the years. And we say, okay, we're going to train the graph on like the years before this date, and we're going to try and predict what's going to happen. Like, how is the graph going to evolve after this date? Like, where are the links going to appear? And it seems to work. It seems to work pretty well by feeding in both graph features. So the one that works really well is common neighbors. So just saying effectively like how many triangles are there that are unclosed. So a triangle would be I'm friends with a shark. He's friends with, what's your name, Manny? Then does it mean that Manny and I will become friends? So that's like the classic triangle. So in this example, it would be person A is co-authored with B, B is co-authored with C. That should therefore mean that C is very likely to co-author with A. And so like that's called computing the common neighbors. And that's like a very, very high, it's very, very simple, but a very high importance feature. Other features that we've played with are running the Louvain clustering algorithm and seeing which community nodes end up in. And if two nodes are in the same community, that seems to be another high indicator that they will in future be connected if they aren't already. And there are a whole load of other variations on these things. So like variations on how connected is your neighborhood to the other person's neighborhood, variations on are you in the same community, variations on what's the shortest path between the nodes. And so there are lots of different algorithms for that. And so this problem is, I think it works pretty well for graphs where the node labels or the types of things are the same. And it's sort of more, I haven't really researched it for like trying whether things that you're predicting are completely different, but that's something that, I mean, there are papers where people have done this as well, but I haven't tried it on any data sets yet. And then the other one that seems to be working pretty well is the graph embeddings that I mentioned before. And there's lots of research in this area too. So we've got Graph Sage, here's one over here. So all of these, the idea is that we're basically like, you could consider them all dimensionality reduction techniques. We've got a graph in kind of this n-dimensional space, and we want to compress it down to an array of values so that we can then feed those usually into a deep learning model is what is typically the pattern that we've seen people taking here. So it could be that there are lots of different ones, and they all vary slightly, and they have different sort of runtime characteristics, and a lot of them only take into account the structure of the graph. DeepGL, this one here is nicknamed DeepGL. And this one is interesting because it not only takes into account the structure of the graph in coming up with these vectors, but you're allowed to feed it like properties as well, whereas a lot of the other ones are purely computed based on the structure of the data. The most famous of these is probably the deep walk one on the right-hand side, and then there are also other ones. We've got structurevec as well. I'm sure there are a couple of other ones as well, but I haven't played with them yet. So that's one other approach that seems to be quite interesting. And then going beyond that, my colleague Andrew and his friend David Mack. So Andrew Jefferson and David Mack have got like a research organization called Octavian, and they've been trying to work out, okay, beyond that, can we like do graph-based machine learning directly on graphs? So like, can we build machine learning models directly in graphs instead of that other technique where it's, okay, take the graph, flatten it so that I can use the existing kind of matrix-based machine learning approaches. And so they have loads of articles and presentations written on their research. And so they observe, like we'll take a simple example. So if we're doing like a regression algorithm, that often comes up with, hey, you build this model, like a very simple model, and it's like, okay, take this feature, times it by this number, take this other feature, multiply it by a different number. So you get effectively like a mathematical equation. And they're sort of exploring, okay, what's the equivalent? If we ran it on a graph, instead of running it on rows of data, what does it look like? Where they've gone so far is it's always like trying to figure out how do I translate this problem into something that I can run on a neural network. So I'd say this is a little bit further ahead in terms of this is probably like where things are eventually going to go, and their stuff. So if you want to have a look at that, Octavian is the name of their organization. Okay, so that's the first category. So that was the top left of our diagram. The second one is kind of just more an operational thing. So this is the idea that, so we've got a quote in here. You can see that not every single problem is embarrassingly parallel, and we can just throw GPUs at it. And what our customers have been telling us is actually having these sort of, I guess, difficult queries to run in the pipeline can slow down the approach. And so the thinking is, well, can we, instead of like doing these joins where we're kind of we're sort of having to join lots of data from different tables together, in a graph, when we query, we only really need to look at the bits of the graph that we're actually interested in. So if we're trying to compute like some features based on a particular node, we can just go and look at the neighborhood around that node. And the speed of that query is related to how much data it touches. It's not related to how much total data that we have. So that's the idea with that one. And here it also means that sometimes we can come up with different ways of solving problems where there's already a defined way of solving it with different technology. So just to give an example, if we were trying to do collaborative filtering, one approach is to build like a massive matrix of item by item similarity, and then we say people who bought this item also bought these other items. A graph variant of that would be, well, can we actually use the graph structure around a person? So we've got this person, we can have a look at things they bought, we can then have a look at other people who bought those things, and can we then have a look at the other things that those people bought? So we can do like kind of almost like a localized search rather than having to do like this big computation across everything. And you can certainly like combine these approaches. So maybe you do some sort of big upfront thing to work out, okay, which things are similar to each other, and then we can use that to get us started. But then we can also make use of a graph to enhance the result that we come up with. And so you can see some examples of that as well. So that one is, I guess the idea is simpler. So we don't have, there's not really much more to say about it other than what I already did. Section 3 is, so this is knowledge graphs, and this one we have a lot of work has been done on this. Knowledge graphs is a bit of a weird one because it's kind of a bit of a buzzword. So people put like they like connect lots of different data sources together, and they're like, there we go, knowledge graph. When actually maybe they're just bringing like a master data type solution or putting metadata together. But for our definition, we're just saying it's a way of connecting data from different data sources into one graph. And we're not saying that a knowledge base is a knowledge graph. And so we've seen people kind of doing 3 different areas, or 3 different types of problems. So we've got context-rich search. So this is the idea that when we're searching for stuff, like a typical way of searching for things would be, can I use like Elasticsearch or Lucene to find me the best document that answers my question? And that's kind of a context-free, I guess you could consider it a context-free way of searching. So it's going to give kind of the same result to everybody. So if I search for this, it's going to give me the best document overall. Where we can apply like a graph to that is, well, can we work out like for this user, like use that Elasticsearch approach or that full text search approach at the beginning, but then can we apply like the context of this user, like what have they searched for before? Or like are they connected to some particular things in our data set that might indicate what they're actually looking for? I think a nice example of this is actually on LinkedIn search, and I don't know what technology they use to do this, but if you go and search for a person in LinkedIn, it doesn't like try to find you the best person with that name in the whole of LinkedIn. It tries to find you the best person with that name who's closest to you in LinkedIn. So if I go and search for like someone called Jim, it's going to look in my network and go, okay, is there anybody who's like level 1 connected to you with the name Jim, or level 2 if not, and it will show you like the person that thinks that you were likely searching for. Whereas if a shock does the same search, it probably comes up with a completely different set of people. So it's kind of taking the context of us and our LinkedIn network into context when you're doing that search. And so that's the idea here. So can we take that context into account? And sometimes this also ends up like bringing in like, can we can we extract some information out of raw text? So can we find the structure in unstructured data and put that into our graph and use that to search? We go over to the far side. NLP is kind of so broad that there are lots of different solutions for this, and certainly the cloud providers have got answers for like the generic case. I think where we've seen people kind of experimenting is where the terms they have specific terms for their problem, and they need to build some specific NLP models to help them here. And a graph database is definitely not the tool that you use to go and run an NLP algorithm, but it can be quite useful for storing the results of that. So if we're doing like an entity extraction, or if we're pulling out the, like in a product catalog, so this is the eBay one, if we're pulling out the things related to different products, we can actually build quite a nice graph of the structured data from the unstructured text. And then, as you can see, we've got some examples of how you might then use that. So the one I know the best is the eBay one, and they have a chat. Well, it was originally a chatbot in Facebook. Now they think they have it as a Google Now type thing, so you can search, kind of almost like search a graph in natural language. So you say, hey, I want to buy a pair of shoes, and it will ask you a question back sort of by traversing in, okay, pair of shoes, what should be like the next thing that I ask? They've kind of built a graph of product data and then working out, okay, what have other people done before you, and what should be the next question I ask, with the goal of, okay, ideally what I want you to do is buy something, so I'm going to vary the question to try and take you down a route that will lead you to buying something. And then if we come back across to the middle again, we've got, can we do entity matching? So can we build like a graph of entities that we extract from data and then connect that with the data that we've got? You can see there are a couple of examples there as well. There's lots of stuff on here on YouTube around doing knowledge graph stuff. So if you're interested in any of these, certainly the ones on the left-hand column and the ones on the right-hand column have like hour-long talks that go into much more detail. Which leads us to the last sort of area where there's much more exploratory work happening. So I'll just show you like an example of like the type of problem where we would want to have it explained. This is not specifically related to graphs. But what we want to do is we want to try and figure out, okay, can we classify the wolf and the dog? And so that's our goal. So we want to train a neural network for these pictures. And so graphs are not particularly anything to do with picture analysis, but these are a lot of the examples of how neural networks can be used to rely on pictures. But what we want to do is we want to tag this as a wolf and this is a dog. And this is generally considered quite hard, but eventually somebody came up with a way of configuring a TensorFlow network that would do it, until it was given this picture of a dog with shoveling some snow. And it's like, it's a wolf, which clearly, like to a human, this is not a wolf. And so this is the problem, like at a very high level, this is the problem. It's like we've got this quite complicated, and you could say this is a graph, like it's a computation graph. It doesn't really have any information in it at all. It just has numbers, and somehow the data gets fed through this computation network, and at the end you get, in this case, like a label, like a wolf or a dog, like, or it would be a 0 or a 1 in positions in an array. But we don't really know, how did you come up with that answer? We could look at the data that you trained your network on, like the images that you trained it on. That would be one thing that we could do. So we could capture that metadata. But we don't really know, okay, and I guess that if we manually explored that, we'd be able to see, okay, you never trained it on images where, or maybe all the images you trained looked pretty much the same. So you never trained it on an image where there was the animal and some other piece of equipment. And so perhaps that's why it's gone wrong, but it doesn't really tell us, okay, specifically why did the algorithm go wrong? That's true, yeah. So it could be that. I mean, when you go to the extremes of some of these, there's examples of people deliberately trying to break it, and they can just change one pixel, and it breaks the whole model in image recognition land. But effectively, at a high level, there are 3 problems to solve, and I'm not necessarily suggesting that graphs are going to solve all of these not particularly in image classification, but this is an area where people are trying to figure out, like, can we do something to explain it? But we want to can we explain the data? So this one is a little bit simpler. It's just like, can we like capture, like, what are we doing? Like, can we build like capture the provenance of how did we train this model? Where did the data come from? Can we capture, store all the different models that we tried and the data that we trained them on? So this is like kind of almost storing the metadata of what we did. I don't know that it necessarily needs to be in a graph, but it can be somewhere. Then we want to say, okay, can we explain the prediction? Like, how did we end up like predicting that was, in that case, a wolf when it seems like it should be a dog? And then can we explain, like in this case, can we explain that neural network? And is it possible to do this without reducing the performance of the algorithm? So if the neural network gives the best answer, but we can get a close enough answer using another tool, maybe a random forest, where you can kind of see, okay, where it will give you like the feature importance of each feature you fed in. Do we choose that one, even if it's slightly worse than this other one, or can we get to the point where we can actually explain the model without reducing performance? So this is like, there's only one like example that we've found where we've seen someone attempting to do this. So they're trying to combine like a neural network. This is in the biology domain. It's a maybe you call it a tool or a product called Deep Tensor. So it's Fujitsu Deep Tensor if you want to look it up afterwards. And they're trying to figure out, like, can we take these computation graph that we've got from the neural network and combine it? And by the way, like when I presented this before, sometimes people were like, okay, how the hell does this relate to images? So this is completely unrelated to images. The images is just a clean example that explains the problem. This is now back to graphland where we've seen people trying to do stuff. So it's like, can I take a knowledge graph where it's built together like this network of the actual data with the computation network of the neural network that we built I guess to try and predict some links or predict like a category of something. And so in here you can see like these are like potentially how you might solve the problem with graphs. This is not something like the Fujitsu things, the only thing where people have really got further. And so it could be for the data, graphs are quite good at data lineage, not particularly graph algorithms, but like being able to capture, okay, where did that data come from? A graph is quite a nice structure for modeling that. In terms of the predictions, can we like connect the nodes in this computation graph with some actual nodes that explain, okay, what does the data actually mean? And then, yeah, then the Fujitsu thing is the last one, really. It's can we almost combine these two completely disconnected subgraphs together to help explain a neural network in terms of English.
Overlaying a graph on top of the neural network?
Yeah, so I think that's what they're doing in this diagram. So they've got like a graph of two different graphs.
Nodes in the graph to specific nodes in the neural network.
Yeah, that's what they're doing. But yeah,
And obviously the question that follows from that is how.
Oh yeah, I have no idea. You know, that's their paper. It's a Fujitsu Deep Tensor for.
They have some way of doing it.
Yeah, I would imagine that it's not a completely generic way of doing it. That you could go and apply it to another problem. I expect it's quite like a specific approach to their problem, and the approach of how do I generically do that is probably way harder. You would think.
I mean, do you think that neural networks are graphs?
Yeah, but I don't think it's a graph that you can understand just how it is.
You would hope. I mean, you've shown examples of graphs, and you've shown where type can be associated with a node in a graph.
Yeah.
And a type with a relationship, and that allows you to do inference. But you would hope that your neural network, that nodes there have some correspondence with something that actually exists in the real world.
Yeah.
But you don't know what that corresponds
Well, I guess that's the problem to solve, isn't it?
Yeah, the neural network has presumably extracted some feature from the world, from the training data, but you have no idea what that feature is. So that's
Yeah.
the thing that makes this problem hard.
Yeah, that is well beyond the mathematical skill that I have, unfortunately.
Well, I think it's not just maths, is it?
Yeah, I've not done anything in this area, so I'm just the messenger of what somebody else has been trying to do. Sorry?
You're making a good point here.
Yeah, but yeah, this is the, I guess this is the area which is interesting, like in terms of people would really like to come up with a useful solution here. But yeah, this is the only one we've seen so far. Okay. So yeah, just to summarize, I guess I'm reasonably close to the end, and then we can do some more questions if we have them. Is that for some problems, like having the context of something allows you to solve it better than not having it. And this is like kind of like it's almost like how do I know whether a graph is going to be useful for my particular AI or machine learning problem? So this is like kind of like some things. So like, is the data like a graph? Like, do you think you have some predictive relationships, or like can you see that the data is split into different components, and we might be able to use those to predict something? I guess the tricky thing here is that people, like often data, the way people see data, they don't necessarily realize that it can be structured as a graph, so it might not be obvious that there is a graph to begin with. But if you can see that there is, it might be that there's something in looking at the structure that allows you to make, to kind of come up with different predictive features than what you can get just from the flat data. And so the idea is like, is everything that you need to predict something just available as like you can consider it as a property, like a discrete property of the piece of data, or are there things related? I guess you could consider it its environment or its neighbors or things that are connected to it that can help you. And so we've covered some examples of that earlier in the talk. The second one is, are we doing so? This is kind of a weird one because if people are really, really skilled in relational database tuning, often they can get these to work fast enough to solve the problems without necessarily needing to use a different database. But one of the common use cases that we see people using Neo4j for is they kind of want to do like these. They don't really know exactly what queries they want to do. They want to be able to do sort of a range of different queries, joining arbitrary things together, often effectively joining tables to themselves. And there's been lots of examples of people like going, okay, for that problem, actually the approach that I can take with a graph where I can basically like query whatever I want and I don't need to worry so much about performance because it's kind of going to be taken care of by the model. For those problems, we found that graphs work quite well. And if you have that type of data, a graph works very well. If you care about the direction of the data, so like if you want to pull in, and particularly with this last point, if you want to pull in data from different data sources, and so I guess I haven't really, I've been kind of assuming that you have a reasonable understanding of graphs already, but one of the nice things that you can do with graphs is you don't have to define the schema up front. So this is one slight difference from when you're doing relational modeling. So relational modeling, typically you go, okay, I'm going to have this table, it's going to have these fields in, I'm going to have this table, it's going to have these fields in, perhaps I'm going to define a primary and foreign key between them. And if I've got a new bit of data, I need to go and define that schema before I bring that piece of data in. With a graph, I guess it's a bit of a double-edged sword. It will literally, by default, let you import anything. So if you decide, hey, I want to go and bring in all that data from that completely different data source, and it's going to have completely different relationships than I had before, it's going to use completely different labels on the nodes, there's nothing to stop you from doing that. Obviously, the disadvantage is you can end up with like quite an unwieldy mess if you're not careful. But the nice thing is you can just go like really easily, like if you want to prototype, hey, I want to see what happens if I bring that data source in, or that data in and use some of the structure that it brings as an extra feature in a model. It's really easy to do that process. So yeah, I guess that's the end of the slide. And this is me if you want to ask me anything afterwards.
Time for questions. Thank you very much.
And I think that you.
You were speaking as if you had the data already in some graph database format. Isn't one of the biggest challenges that there isn't, a market winner graph database that everyone can agree to use, and there is, I would guess, I'm not up to date, but I would guess a minority of
Yeah.
There's a major problem with actually getting the data organized into formats that you could then do this focusing on.
Yeah. You are indeed correct. Yeah, getting the data from wherever it is into this format is, yeah. I wouldn't say it's an unsolvable problem, but yeah, that's like the first thing that people come across.
It's a large problem.
Yeah.
It's like rewiring the London or something. It's that kind of scale of problem.
Yeah, I think what I've seen and seems to be the trend is that you don't necessarily have to translate. You don't need to use a graph for all your data. There are some and typically the trend is okay. Well, what we see is people are often using multiple databases, and this will be solving one particular problem that they have. And I think when it's like that, it's a bit of an easier problem to solve because it's not like I need to figure out, okay, how am I going to replace every single application with a graph database? It's just like, oh, okay, for this particular problem, a graph seems to be a good fit for the problem, and I just need to figure out how do I get my data for that problem in here.
You could end up with multiple different graphs, but with no guaranteed consistency between them.
Yeah, so I think that's like at the moment in Neo4j at least. So I'd say out of the people, there are obviously percentage-wise, there's very few people doing graph stuff as a percentage of people doing data or data stuff in general. Of those people who are doing it, I'd say the majority of them are probably using Neo4j to do their graph work, probably because it's been there the longest and I guess it's probably the most accessible of them at the moment. There are certainly other.
I mean, you talk about this more often, but I mean, there are tons of non-SQL databases
Yeah.
which are partially graph-oriented, if you want to look at it that way.
Yeah, I guess it's a whole different talk. There are certainly, yeah. I mean, like the history. I guess the history of the database world seems to suggest that you sort of seem to end up with 2 or 3 on each category eventually.
So the example you got just now on crime fraud.
Yeah.
One of the classic examples is money laundering. So you have a list of transactions A, pay speed, but normally it goes through a number of intermediaries.
Yeah.
And to do that in a relation query, you do an set join on a lot of the tables and transactions, and you very quickly blow up.
Yeah.
Whereas in a graph database, it's very natural, and you can detect those circular loops very, very easily.
Yeah, I'm
At
sure you're
very
right.
high speed. So when we look at those type of things, we will translate the transaction database into a graph database, and then we query it on the graph. So the 2 databases are connected. Same
Right.
with, I don't know, another example is when we look at network flow graph to detect intrusion into a network. You can see machine A talking to machine B talking to machine C, so IP connection. And that is a very natural graph representation, and you can detect fraud in our network very, very quickly. Just 2 use cases, and we can't do that easily using relational.
No, of course you can.
Different tool for the jobs.
More questions?
And is it possible to do online transaction processing with graph database?
Yeah, so I think most of the stuff, the users of Neo4j are using it to do that. Say more, I don't know, I have no idea what the percentage of people doing stuff is, but yeah, more recently we've started trying to add in, actually coming from the other end, more people are doing transactional processing, and we've started more recently building the tools to allow them to do analytic processing on the data. So yeah, there's a lot more people are doing kind of those localized queries that I was talking about, where it's like around a particular part of the graph. And at the moment, the database is optimized for doing those queries rather than doing these big analytic queries where I want to consider the whole database. Yep. Yeah, well, no, you have this, or someone has the slides, so yeah, you can. You just won't be allowed the slide with the child in.
Not for the BCS way.
Yeah.
Do you use any particular tools for creating your graphs?
For importing the data? Or depends where the data comes from, I suppose. So like Oh, for editing, for like writing queries? I mean, there's
For
like,
creating of original knowledge.
So you know you have database IDs, right?
Yeah.
For the relational databases.
Oh, okay, yeah. Yeah, there's not really a client-side tool that matches any of the relational database ones. What people are mostly, we have like a browser-based tool like that people edit things in. I think it's all right compared to other ones. I'm sure it doesn't have every single feature that you can get in like SQL Management Studio or anything like that. There are also some like plugins for like some of the common text editors, so Atom and IntelliJ, where you can get it to, I think even the one you can get into some of the JetBrains tools allows you to administer the database from inside their like editor. I've only used it for syntax highlighting of queries when you're writing it. For like importing data, we have a tool called the Neo4j Desktop where you can, it's like a Electron application where you can manage all your databases locally. I'm not on my machine, so I can't. I guess I can't show you what that looks like. But if you download it, you'd be able to see. It's basically like an app. You've got all your projects, all your databases. You can control them all from this one application. And there are a bunch of, we have what we call a graph app. So they're like add-on applications that you can add in to do different things. And so we have one which is an ETL tool, like an ETL UI, where you can connect it to a relational database and choose which tables you want to import, like what graph structure you want to create from that relational database, and it uses some rules to try and predict how it thinks you might translate the different primary key, foreign key relationships that you have in there into a graph structure.
Have you seen people translate real-world databases relatively easily into graph databases, like simple ones where there might be a bunch of tables and some relationships between certain columns, and it's known, and maybe sometimes the graph database can see the name of the columns match, so there might be relationships.
Yeah, so in that tool, it's just looking at, it makes like some predictions. So if it sees a table which has two foreign keys to two different tables, it goes, okay, that's probably a join table. And in graph database land, that would be just like, there's not really a need to have, you can just connect the nodes directly to each other. You don't need to create like this extra thing in between. So yeah, there are a few rules that they use to do that. And yeah, I've seen people been able to successfully translate data across. To link back to what I was mentioning before, they're not like taking the relational database, all of it across. It's often like if they're taking, it's like some subset of the problem. So to give you an example from a few years ago, so I'm a bit further, I work in our developer relations team, so I'm further away from seeing what exactly customers are doing with the data, and they tend to give you the best stories. But I used to work in that area, and Shuttle, who then got bought by eBay, were using 3 different databases. They were using a relational database, a graph database, and a document database. They were using the graph one specifically for working out like when the delivery part of their problem. So you could go and so they were using Mongo to store so people could or like they had Argos as one of their customers, and so it was like Argos if you wanted to do same day delivery, you could have that through what's called Shuttle, then became eBay, and you could request that. And so the actual request for, hey, give me a time slot was like a multi-dimensional query of, so they were effectively acting as a layer on top of a bunch of couriers. So they needed to go and work out, okay, where are you? Or where does this product need to be delivered to? Where's the warehouse that has the product? Which of our suppliers do that area? What time slots do they have available? So you kind of got this almost like multi-dimensional query. And so they were doing that particular part of the problem in Neo4j, but there was a whole other part of the problem which was nothing to do with Neo4j. So keeping track of the order once it had been done, that was all in document database. So they were storing the request in there. And then afterwards, when they were doing analytics on it, they were actually much more familiar with doing analytics in MySQL. So they were actually just taking that data from document database into MySQL and doing it over there. But for the actual hey, this complex query, which was originally, they got it down to 10 lines of Cypher, which is the graph query language, and they said it was able to run significantly, was able to run in a way that they could get a result while the user was waiting. And so, they were pretty skilled relational database tuners in their company, so it's not like they didn't have any idea what they were doing. but their favorite, or their quote that our marketing team were very happy with was that their fastest delivery, so like from the point of a customer had ordered it and had the good delivered, was quicker than their slowest query had been before they started using a graph query. So it was like 13 minutes to go and do this crazy query, and they had got the query done and the order delivered into the person's house before the query had finished. So, but as I say, it's not like the whole problem. It's not every single problem. It was like a problem that a graph is really good at solving, and they used it to solve that. So that's the where a graph works really well, is kind of where you're not really fighting against it, and it's kind of a natural solution for the problem. But equally, yeah, it's not the solution for every single problem. But I guess that's going to be the same for any technology. Yeah.
From your perspective as developer relations, then, what's a typical day in the life of a Neo4j developer? What kind of things are they thinking about in their day-to-day work, and how they're
People using Neo4j, or people me or
No, about your developer relations. So your developers, what's their thought process? What are they going through every day and thinking about?
people building the actual Neo4j, the product?
Both.
You're talking about users, aren't you?
Oh,
Are the users developers as well then? Are they coding?
yeah. So the people actually using Neo4j, the database itself, would be application developers interacting with the database in some way, more often than not. So I don't know. I guess it depends on what problem they're solving. I mean, this is
concerned more with the building of graphs from non-graph data, or are they concerned more with analyzing the graphs once they've got them?
probably more what they can do with the data once it's in there. But equally, as you've pointed out, like getting the data in there is the first problem. So they obviously do spend some time trying to figure out how to do that. It's kind of a mix, kind of coming back to what Ashok was asking before about, it's kind of a mix between people doing analytics stuff on it and people actually just using the graph database as a backend to a website that they're building. And yeah, the user of the database itself is going to be an application developer, and they would be interacting with the database via a driver, like some sort of driver usually in a programming language. They wouldn't usually be writing queries directly against the database. It's more likely to be from an application that's executing that on their behalf. From the Neo4j developers itself, it kind of depends what part of the product they're working on. So if they're working on the drivers, they're trying to work out, okay, how can we make this experience really good and similar across all the languages? If they're working on the kernel of the database, they're trying to work out, okay, how can we reduce the memory that's being used? How can we make things faster? If they're doing the query language, they're kind of the same thing there. How can we make these queries execute faster? How can we make them take up less memory? How can we design this query language in a way that is really like declarative for graphs? What do we need to do to extend this to solve more problems? And kind of one of the sort of cross-cutting things as well is how do you make life easier for people using this tool? That sort of goes across all of them. Yeah, and in our developer relations team, we're trying to figure out, okay, how can we, like our goal is, we're sort of like, can we get more people to use it? So we're trying to figure out what can we do to get people who aren't using graphs to use graphs to solve a problem. So I guess everybody has a slightly different position and angle on what they're trying to do. I have no idea if that answered your question or not. Okay.
Okay, I think then to the end. Thank you very much.
Cool. Thank you for